So in the last video, we brought up this topic of curl, which basically is another tool that we have to analyze the properties of a vector field. You know, we can talk about vector fields being conservative or not. Now we can talk about whether or not a vector field is going to be swirling in a particular direction or not. And one of the last tools that we need to kind of build up to the final topics in this class is this tool which we call the divergence. And it's the divergence of a vector field at a particular point. And so let's just kind of give a brief definition. So the divergence of a vector field measures, if we're thinking about it in terms of heat or water flow or airflow, it measures the tendency of the vector field to either go away from a point, which means that point is what we call a source, or to kind of be attracted to and or to come to that point. In which case we call it a sink, kind of like a black hole, right? A lot of things get sucked into a black hole. We call that a giant sink. And so one of the best ways to think about this is kind of like heat. You can think about it like a light bulb or a refrigerator, right? If we have a vector field and we have a point in this vector field, and a majority of the vectors, maybe there's a couple going in, but a majority of them are kind of heading out away from this point, then on average, we would say this point has positive divergence. Okay, positive divergence, which means that this point here is what we call a source. So that means if we were given a schematic by a company and they said, hey, we're not going to give you the object, but here's this vector field that kind of represents how the heat is moving around. Could you figure out where we're going to need to put, like, say a cooler in our system, right? Where are we going to need to cool things down? And if you determine that there's a heat source by calculating the divergence, right? If you determine that there's a heat source right here, that things are radiating away from this point, they're emanating away from it, maybe that's a good idea to probably cover that point with, some sort of heat absorption, right? Something that's going to absorb all of that radiation that's kind of coming out. And likewise, if on average all of the heat is kind of localizing at that place, maybe you don't need a sink, right? Because it is a natural sink, right? So if all of the heat on average is heading into this point, right? Or if you're thinking about maybe hurricane winds or something, and they're kind of centralizing around a certain point, maybe you could put something there to capture the heat that way. Or maybe you won't need it because, you don't need a tool to capture the heat if it's already naturally just kind of pooling there all on its own. So this, again, is another way of talking about vector fields. Obviously, in the last one, we determined if the vector field was going to experience some sort of rotation, right? Would the water be rotating? Is the heat swirling? What's going on? Now we can talk about if there's specific points that act as sinks or sources. And so divergence, in kind of a secondary way of saying this, it's kind of, let's see. It measures, how much of the change, how much of the change is going in the direction of F. Okay, and so what does that mean, right? What does that mean? So let me clear up this drawing really quick and kind of try to illustrate what that means. Let's say we have a point here, and around it we have some vectors. Okay, we have some vector, and let's say the next vector is kind of going out this way. So there's like a little bit of change happening kind of there. And let's say there's another vector and it's kind of going this way, and there's a little bit of change that has now happened in that direction. okay? And the idea is that if we add up all of those little bits of change, okay, we add up kind of all of those little bits of change, then whatever we get when we add up all those pieces is going to basically give us the overall tendency, to either kind of head away or towards a point. And very similarly to curl, the way that we calculate this is, well, last time I checked, if we want to evaluate the amount of change going in the direction of a vector field, we could use this formula right here. So it turns out that this is just going to be the del operator again, d dx, d dy, d dz, and then dot our vector field, which has a p component, a q component, and an r component. And so this, right, when we calculate it, is going to give us dp dx plus dq dy plus dr dz. And something to point out here is that unlike our curl, which results in a vector, this right here is some number. This is a scalar quantity, okay? And if it is a positive number, that means that this is a source. That means things are headed away from this point on average. And if it is a negative number, that means things are attracted to this point on average. So you can kind of think about it in terms of magnetism, right? It either means things are going to repel or be attracted. So for example, we could do a quick example here. So let's say, for example, you're given the vector field f, and let's make this kind of an interesting one. So let's do e to the x times z, comma, cosecant of z, comma, sine of xz. And I would like you to calculate the divergence of f at the point 0, 1, 2, at the point 0, 1, 2. Let's do it. So if we just use our little formula that we got, we take the derivative of the first term with respect to x. So we're just going to get e to the x times z again. Take the derivative of the second one with respect to y, which we're going to get 0. And the derivative of the third one with respect to z, which is going to give us an x cosine of xz. And now we just have to evaluate it at the point 0, 1, 2. So if we do this, it looks like the first component here is going to end up being 2. The second component is still 0. And the third component is also going to be 0, so it looks like the divergence is 2. So that means in this particular vector field, which is in 3D space at the point 0, 1, 2, it looks like there's a little bit of a source, right? That things are going to kind of be radiating from that point on average. Okay, and so this is what we call the divergence of a vector field. Now, if we want to kind of figure out how we're actually going to use these things, like we showed that curl kind of manifested itself in the form of Green's theorem, it turns out that we can use divergence to calculate something else that's kind of interesting. And we call it the flux of a vector field through a particular path. And so we're going to start teaching this in 2D. I'm going to save the 3D case for next week, but I'm going to start teaching this in 2D. So let's imagine that that I have some sort of closed line integral. Okay, we're going to keep this simple, and let's just say that we have a closed line integral. Okay, a closed path. And let's imagine that I want to determine on average through this path, is the vector field going out through this path? Is it going out, or is it coming in? Are we passing through the wall of this path, like by coming in? And the very classic analogy is if you imagine that this is a net, right, for catching fish. okay, you want to place your net probably somewhere where the water is on average, it is centralizing inside of this net, right? That would be a good place for you to place your net because that probably means there's going to be more fish there. And likewise, you probably wouldn't want to put your net somewhere where the water is always just like headed out like so, because if it's headed out from your net, right, if it has a tendency on average to kind of just leave this entire region, okay, as a whole, then you're kind of picking a bad place to put your net. And so this idea is what we call the flux. Okay, this is what we call flux. So flux, kind of loosely, it determines, okay, in the 2D case, it determines how much of a vector field moves perpendicularly or orthogonally, to the path C. Okay, and now let's kind of think about this in a couple ways. Okay, so there's two ways to kind of think about how to go about calculating flux. The first way uses the definition very literally. It says, okay, what we can do is at all of the points on the boundary of this shape. So maybe I'll just erase this shape entirely and I'll redraw it really quick. So, here we have our closed path C. Right, here's our closed path C. What we can do is at every single point on this path, right, there is a vector, okay, doing something, right? There is some sort of vector doing something from our vector field. And what we are interested in is how much of that vector from our vector field F, how much of that vector is going orthogonally, right, is going orthogonally to our path C. That is what we are interested in. And the way that we can represent that is we want the amount of the vector field F that is going in the direction of the unit normal vector little n, which we learned in Calc 3, okay, on this curve, which is given by ds. So I'm going to write this down, and I'm going to say it one more time. Okay, so this right here is the 2D variation. This is the 2D variation of flux. And it basically says, remember, if we want to figure out how much of the vector field is going in a particular direction, it's the vector field dot. Now we need something that gives direction, and we need something that gives magnitude. Okay, and so this is something that we've been kind of a trend that we've been following this entire time, which is that we need direction, we need magnitude for any of this to make sense, and this is how we go about doing this. And so we could follow this down the rabbit hole where we have to remember from Calculus 3 that the unit normal vector n, the unit normal vector is given by this vector d. So let's think about it. So it's going to be dy dt, comma negative dx dt, divided by the magnitude of r prime of t. So let's try and remember where this comes from. If we parameterize this path C using the vector r, okay, and the vector r is just, it has its own little component, x of t and y of t. Then if we're talking about coming up with a normal vector, we need the slope, which is the derivative. And that, you remember that r prime kind of does this. R prime is going to give us, dx dt, dy dt, like so. But to get the perpendicular slope, it's like the negative reciprocal, right? So the negative reciprocal gives us this, gives us this green vector here, And then, of course, we have to normalize it. We have to turn it into a unit vector by just doing the dividing by the magnitude of r prime of t. Okay, so that gives us our direction over a little chunk of our curve, which is given by ds. Okay, so this is how we do this. We can go ahead and plug things in. So in order to calculate the flux of our vector field F, okay, we can plug in certain things. So this is, dot, then we're going to have, dy dt, comma, negative dx dt. Now in the denominator, we have magnitude of r prime of t. And now we just have to remember that ds is like that square root of dx squared, dx dt squared plus dy dt squared, etc. And that we were able to write in the form of magnitude of r prime of t dt. And so it turns out that to calculate 2D curl, it's actually nice and simple. Things do cancel, and we get f dot dy dt, comma, negative dx dt times dt, and we can use this formula to do it. So this is one way to do it. Okay. Now if we keep going, with this, what do we get? We're going to get closed line integral of, so the dt's are all going to cancel, and so we're going to get our f, which is, again, consists of p and q if we are in 2D, dot dy, comma, negative dx. Well, this is actually just going to become, it's pretty simple, so closed line integral, we get the integral of p dy minus q dx. And if we use Green's theorem again, this turns really nicely into a double integral over d of, and what does this become? Well, it becomes dp dx plus dq dy with a little dA on the outside. Maybe I'll scooch this over. dA. Okay, now, if you're a little confused how we got here, there's a file in files for Canvas that you can go ahead and look and just be like, oh, this is how we got it. But this is just Green's theorem that we got this way. Green's theorem. Okay, now this hopefully looks somewhat familiar. This right here is the divergence of f for the 2D case. Now, why does any of this make sense? Maybe you got a little lost along what we were doing, so let me remind you of what we were doing. We learned about this thing called divergence, and I was asking you, if I took kind of a netted region, kind of a closed path, okay, and I wanted to know the tendency of our vector field to either be kind of coming into that closed little net, that closed little path, or to be headed away from it, we said, okay, so basically what we're doing is we're adding up all of these little kind of these tendencies to be orthogonal, right? How much of the vector field is going orthogonally to the path at any given time. And so we started off with this little closed line integral. We're like, okay, this makes sense. But option 2 of thinking about this is just basically what we're doing is we're just adding up the divergence of f, over the entirety of this region D. Now, what about all the points on the inside? Well, very similarly to how curl works, if you're at that point and you determine that the divergence, say, heads in this direction here, okay? Right, that there's little bits of outward pushing like so, and you calculate a value for divergence, and you go over to the next point and you calculate the divergence there, and you calculate all these little points that are pushing away, and you go to the next point and you calculate the divergence here. Hopefully you're kind of seeing a trend that the divergence is all on the inside, that those vectors, the kind of opposite pushing, are going to all cancel each other out if they're on the inside. And the only time that we're going to get points that don't cancel out when we do our divergence calculation is actually going to be right here on the edge. Okay, it's the only place that we are not going to get everything to cancel out. It's going to be right there on those boundaries. And we can determine whether or not we are going to get inward movement or outward movement. So flux can be thought about adding up all of the divergence inside of this region D, and it kind of naturally lends itself to this definition. But we saw that if we kind of went on this merry little mathematical journey, we did indeed end up at what we call what we will later call the divergence theorem, which basically says we add this up, just like in the last video we covered how if we have curl and you add up the total curl, that's how we get Green's theorem in the first place. So I want to pause here. I think this is enough for us to go off of. I'm not going to, lie to you guys and say that this stuff is easy. It's a little bit challenging. I would recommend watching lots of videos, reading things, going onto Canvas. I'm looking at my nice little cheat sheet that I made for you all to use when you're talking about, when you're doing the quiz and studying and things like that. Check it out and see if it makes sense. Try some of the problems. And if you have questions, post them on Canvas sooner rather than later. All right, so next week we're going to start talking about parametric surfaces, doing all this stuff in 3D, and then we're pretty much at the end of the class. So the end is in sight. Keep up the good work, and I'll see you all next week.